Okay, so today we have about 25 sheet notes to go through. You can see here at the bottom, so we should be fine to really within this hour and the next hour to cover them well. They kind of reinforcing what we talked about last week, but this week we're going to look at the construction considerations, which you can talk about when answering your assessments or any questions that we may ask you about portal frames. Last week, we mostly talked about the design impact, which can be strongly related to constructing the building or the structure, those industrial structures, portal frames more specifically. So today, we're going to look at the construction. Some of them you're going to see very related to what we talked about last week. Some of them is, for example, you will understand why purlins or girts are placed in particular direction as a construction reason, and some other cases to talk about. Then hopefully when we're done with that, we will start going through the workshop questions, which is part of your the assessment question, assessment 1, which you're supposed to be starting on. I will start going through them. So we have last week 3 document for the workshop questions, but you can see it was expected that we go through the 5 questions last week during the workshop. I think today we should be able to cover some of those first questions. So today we will aim at going through the first 3 to 5 questions. That will happen today in the second hour. And tomorrow, during the workshop this week, we should be able to be on track up to question 9. And again, you're supposed to be working with your team members to answer them properly. That's about our assignment and what we're going to be doing today. Any questions? Someone try to ask something? No? Okay, so let's see what we need to know about industrial buildings. This is just the same front page. Again, we're going to be using some of those documents. These documents are reference, which are strongly related to such developments, and you can save for your future reference. Today, we're going to be using one of those documents in determining the size of purlins or girts to have in a development, okay? So what does that mean for you and for the subject? You may be asked in a test or in a final exam about such process, and because we use such documents, so we consider that it may come to you in a final exam. But as I said to you, there's a lot of reading materials or some reading materials which we give you. If we don't use them and practice them together, don't expect them to be coming in the final exam, because we gave you more than required. So we're going to run through these items and talk about their construction considerations. Same thing, portal frame layout, which we started talking about last week when I said to you, there are different ways of deciding on how to place the bracing at roof level. Depends on, again, the architectural impact. Do they really want the sunlight to come in or not, etc. We will talk about roof and wall sheeting. Yeah, sheeting, which is the cover, and sheeting is basically supported by the girts and purlins. So sheeting is just the finish that people see from outside. Who carries the sheeting? Purling for the roof carries the sheeting, and the girts for the walls, they carry the sheeting. We will talk about bridging. Bridging, they are not bridges like what you see in the roads. No, bridging, they are elements which really helps purlins and girts to work better. We will look at this, more specifically purlins. So the bridging, they are just elements that will provide constraints to the purlins, and we will look at these things. Now, So before we start going through the purlins, I just want to, this was just a sketched kind of diagrams, just reconfirming your understanding for what we mean with a portal frame. Can someone tell me which image, okay, is a portal frame? Which image or which sketch, which hand-drawn sketch is actually a portal frame? Just tell me first column, middle row, first column, or I mean the left column, middle row, or top row, or lower row, or the right column, etc. Yeah, can you just think with me about this? Again, which frame from what I've been talking to you about is actually a portal frame based on what we talked about last week? So I can't hear you well.
Second column.
Third.
So which, okay, let me put numbers. I'm not really getting the, when you unmute, it may take longer. So when just, it's not. So take this as 1, 2, 3, 4, 5, and 6. Which frame sketched in front of you is actually a portal frame?
4 and 5.
I can't hear you. Sorry, really, it's not loud. What was it?
4 and 5.
Correct. Yes. Yeah, portal 3. Portal frame 3. Yes, that's the one. So why did you say portal 3? This is a portal frame. Why you said the image or graph or diagram 3?
Maybe because it's supported with the stiff joints.
That's right, yeah. So the connection, or in other words, the connection between the rafters, we call this as a rafter, and between the column, which is also called a portal column because it's part of a portal frame, they are welded. They are fully welded, or in other words, we can say it's a rigid joint. Because this is a rigid joint, not pin, then the frame itself will look after itself in terms of resisting lateral load. When it's pushed by wind or any lateral loads, the portal frame should be able to stand. It will sway a little bit, but that's what the engineer is going to calculate. It's going to sway a little bit, go like sideways by 20 millimeters, 25 millimeters, but that's what the engineer is going to calculate and make sure it's acceptable. If the swaying is too much, they will design more stronger columns mainly, or even they can design stronger rafters. So basically, that's the simple way of understanding portal frames, and that's what we talked about last week. We talked about different ways of creating or developing this. If you remember the joints and welds, it's more expensive. And another understanding you need to understand is all sort of actions, right? All sort of actions, which how many actions we said can be on the beam, on the rafter, how many actions we can have. Yeah, can we summarize them quickly? What type of actions? We can have axial load thereafter, that's one. We can have shear load, which will tend to cut. So axial load, it's along the rafter. The vertical load, we call it shear load, it will tend to cut the rafter. And the last one was, what was it?
Bending moment.
Bending, correct. A bending, which can be either clockwise or anti-clockwise, depends on the wind. So the connection you're going to be constructing here will be able to transfer all those type of actions from the beam to the column, and that's another way of thinking about it. And some of our questions will ask you to think about this as well. Now, this is unlike, obviously, all like this sketched one here. This is a pin joint, cheap pin joint. Is just very just 2 bolts with a cleat. That's it. We don't have stiffeners. We don't have all those detailing we talked about. However, the problem with this one is if you push it, if you push it with wind load, it's gonna fall down. So what we do to keep it static, we put a member like this if architecturally possible. Another option is you actually build a block wall. You build a wall, which is maybe not acceptable architecturally. Another option, you put an X bracing, which also, so that's what I'm talking about. This one, just control the voice here. I'm just hearing some sound in the background. Okay, so number 6, someone will tell me how this can be static here. Here, for whatever reason, you can have a moment connection with the ground. So yes, it's a pin here. It's pin, like cheap connection at the support, but this is what they did for this column. They're actually going to use very deep pile or very big footing, so it will act as a cantilever sticking out from the ground. They use this a lot for, you know, for the rail you see in the rail station. Yeah, sometimes they got these frames standing. Or for example, can someone tell me a good example we always see every day? You know, the hoardings when you drive in any highway, you see all those signs, the big road signs, the speed signs. Yeah, they all basically frames. And it's maybe, but I know if you look at them carefully, you're going to see very expensive connections. For whatever reason they do that. But what they are strongly fixed into the ground to resist any actions there. So it is an option, but it's not a typical option for our industrial building, the warehouses we're talking about. So yeah, that's just number 3 is a portal frame. It is a portal frame where the footing is possible to be pins, and the connections between rafters and the columns can be rigid. Steel portal frame. Now it's again, you all know that. That's another sketch which can help you to understand it, and you're going to know more about it, and you're going to do it. So basically, yes, the connection between the roof rafter and the column, it's a rigid connection, and most likely you're going to need a hunch. As we said yesterday, bending moment diagram for this can look something like this. If you have, you don't need to, for this subject, plot or calculate bending moment diagrams, but basically bending moment diagrams can be graphed like this. Sorry, sketching is not perfect, but I'll try to make it as clear as possible. So here we're going to have pin, because it's, if you remember in engineering, because we may have pin here at the bottom, so that means you got 0 resistance to moment. It's like the door hinge. When you want to open the door gonna open with you because it resists no bending. Same thing, if you have constructed a cheap connection to the footing, then expect 0 bending. Then bending will be with a capacity at the, well, it's straight. It's not handy. Yeah, it's gonna be like this. So that's the bending diagram. Then the bending diagram will go like this. Then it can be curving and going to negative again, and same thing, it's gonna look like that. This is the bending moment diagram. All right, so what I'm trying to say, why someone would ask me why we're using a hunch here, because here we have negative bending, and usually the value of the bending here is very high, much even, maybe my drafting is not right, this should be less, right? So this is too much positive bending. Usually this positive bending here, it's less than at the ends, and that's why at the ends we need more. And we talked about this last week as well, right? We talked about, yesterday we talked about, as a design concept and concentration, we talked about the splices, right? And I told you splices, that's what the builders, they say, I cannot, for whatever reason, you couldn't find a way to bring all this half in one go in a truck. You couldn't bring it on site. This half of the portal frame. And it's gonna, someone will say, can I build a column alone? Then this, it's again a cost and time. You don't want to let the contractors spend a day to do that. You just want to bring, you know, because why? This is again what we said about this. This is an expensive joint, rigid, consists of a lot of welding and bolting and stiffening. So as a quality control, it's better to do it in the factory and get it craned. Doing this on site where you need to have scaffolding and all that, you may miss the quality. So it's a good idea to make this joint in the factory and get it trucked and build the frame. So the option here is you have to build all this, and it's still too long. What you can do, you can decide to make a splice here. That's an option. So you can have this smaller part. Maybe this is about 15 meters high, and this is going to be just 2 meters. You can put this, build maybe 20 of them in the factory, put them in a truck, bring them on site. And that's what we're talking here about when you're going to consider the construction. Okay. And you can have another rigid point here, which can be bolted or welded. It's not one way. There is no one way, one steps to do it. But that's where, as I said, with these top type of projects or larger or even sometimes slower, the construction engineers are required to be involved during the design phase, because you don't need the engineers to design all your projects without considering it here, because they have to design it for you. They have to tell you how many bolts, etc., etc. And I talked to you last week about which side to do first. Okay, whether this side, you know, I showed you this, which one gonna carry which. Right? Any questions? All this kind of talks that I'm doing with you today can be used when you answer the questions you have to answer for assignment 1. Okay, so obviously I did already give you hints about how to decide on splices, and you need to use such thoughts when you're going to be showing us one of the final last questions in your assignments, asking you, show me the construction sequence for the portal frame. And that's what you need to think about. Okay. So there, as you can see here, we have on the sketch the maximum transport limit for a particular type of trucks, which will help you to fit it in the back of your truck. We all have been talking about this for 2 to 3 weeks. Basic characteristic of portal frame, it's top connections. When I say top, between the rafters and the columns is rigid. Yeah, and to make it cheaper, like you don't need to say, and that's where I see students get overexcited and they assume everything is rigid. They will tell me, you know, the project where we had a data sheet to look at, and that's what I briefed you yesterday about. You have to read what this connection is. Some people, when they answer me, they tell me this is rigid and this is rigid and this is rigid and everything is rigid. But that was not the case. That was not the case. Okay. And as we're saying here, to build those structures efficiently, we don't need to spend a lot of money in making rigid connections. We're just going to do pin. And as you remember yesterday, pin can be just on-site, a drill, and epoxy, just use chemicals. Okay. So you pour the footing, the gray concrete footing in the ground, and you just bring your column and then just make holes. And that's it. on site. You don't need to prepare the cage, which I showed you another example. Cladding and roofing, I just mentioned that to you. The purlins and the girts, they're gonna carry for us the cladding, whether on the roof or on the wall. Okay, and again, we talked about the transportation limits. We typically gonna be guided. That's what needs to be considered mainly by the construction engineer. Okay, so basically, as I was saying to you, to avoid, because contractors to work at high level, which you're gonna, to make it workable, like if you're gonna think about having contractors to do the welding, this all welding on site, you need to make sure the safety considerations are all met. You're gonna be putting scaffolding around each column, the height issues, the fencing issues. This is cost, this is time. You know, I'm gonna need special engineers to come and check that those scaffoldings are safe. And you can't imagine doing this for each column. It's just going to be a lot. So that's what I was saying. There is a key consideration for construction engineers to make this joint in the factory and get it delivered. Right. Yeah, this is just an overall image which helps you guys to understand where is what. I think I kind of mentioned most of those things over last week, and you can see them now in this 3D view. This image is taken one of the industrial documents which I shared with you as a reading document, right? And you may use them to sketch things in assessment 1, but please don't just copy this and put it in the. I'm not asking you to tell me what is a portal frame. I'm giving you a real project and asking you some construction questions, which is the questions engineers would be thinking about on daily basis when they build structures like these or any other type of structure. But we're just going midway in terms of complication. All right, so I think I don't need to ask you here. It's all written to you. These are the girts. They fixed to the columns. This guy, we call it roof rafters, and it can consist of a hunch. It can consist of splices at the ridge. You've got the purlins. One of the things you have to understand, the purlins are actually lapped, because the purlin does not go from one end of the building to another as one piece. It comes into pieces. And when we connect them, we don't stop a purlin then start at the same point. We have to lap them together. Any idea? Anyone from you can tell me why we have to do the lapping? So if I make a sketch here, think about it while I do the sketch. If I cut here through here, if I cut here, right? And this is going to be your roof rafters. It's just going to be maybe an I section like this. Yeah, I'll try to draft it as clear as possible. Then there is a piece of steel, which is, we call it a plate, right? With ideally 2 bolts. And then behind the plate, I'll make it with a different color. You've got what? The purlin. So it's got 2 lines because it's a C channel. And this one. What I'm trying to say to you, just let me draw one side of the purlin. The purlin will stop here, and then we have to lap it with another purlin to go forward, because the purlins cannot run all the way. Any idea why we lap them here? What's the design or the consideration that we lap it here? What type of bending we have on the purlin? Now, all the bendings I was chatting with you about or talking to you about here, it was bendings on the portal frame. But here, when I'm talking about the bendings here, I'm talking about the purlin itself. Can someone tell me what type of bending we have at this location here? At this location, what type of bending we have here? This is the questions I'm asking you are that's how we're gonna ask you. They are very randomized, very. But what type of bending we got here? Any thoughts? Any idea? Do you know? You forgot engineering? So as I said to you, I made a section here, but so this rafter, this one here, it's actually this. And at some stage, we can have another one here. So let me draw another one here quickly with the blue color as well. Let me just do it like this simple eye. All right, and what I was trying to say, same thing here. We're gonna have another. The scale is very basic, so don't worry about the scale. But nobody knows what I'm talking about in terms of bending. Bending moment diagram, usually it goes negative at the support and goes positive between the supports, like this. Right, this is positive and this is negative. So lapping above the support means how many purlins we got effectively. This is a simpler question. How many physically, how many purlins you have flying over or connected to the rafter? Any idea? We got 2. Can someone talk just to make sure I can hear you? Because I'm not sure. Can someone just talk to us just to make sure we are all online?
16.
Okay, so all good. Thank you, Joe Mace. Yeah, so yeah, the bending or flexure on the purlins, they are basically negative above the supports. And when they are negative above the support, it means that, and they are, as I said to you, they are typically higher. And that's why it's going to be an advantage to have 2 members lapping to each other at the support. Okay, so that's just you just link the design consideration with the construction consideration, and it helps engineers to know what to check and verify when they plan of building things like this. Just let me clarify something because people may be confused about it. It's someone will tell me this part we don't have purlins. It's not meant to stop. It's just for this image. They stop them to clarify how the bracing works. So don't expect purlins to stop here. They should continue. Yeah, the purlins should continue above the roof, but they just stopped it here in this image or in this diagram to let you see what the roof bracing. This is a roof bracing here. These elements, which I can't see. They actually did not mention them. These X, I'm not sure if they mentioned them anywhere. No, I can't see that. So this member here and that member is the roof bracing. This member here, it's between the roof bracing and it's a strut. Takes the compression from one side to another. And again, this strut, one of this main, it's going to make triangles to let the roof trusses work as the roof bracing to work as trusses. And you all understand from engineering knowledge, trusses is about creating triangles. Okay, so there's a triangle here. There is another triangle here. And there is a third one here. So yeah, if we didn't have a strut, it will not do the job. It won't be a truss anymore. Same thing, the eave strut, which we talked about last week. We have it there for two reasons. Number one, to create the trusses with the roof, triangles with the roof, and eventually the trusses. And also what? Give me this answer, please. I said it slowly yesterday, and remember you understand me. So one reason, there are two functions for the eaves strut. One of them is to create the triangles and eventually trusses in the either the roof or the wall system. But I'm asking you, what else we using the eave struts for? What do they do as well?
To carry the girts.
Perfect. Thank you, Ivan. Thank you. Yeah, to carry. There are some dropped or tension rods come from the eave structure, and then they're gonna help reduce the sagging because those girts will sag. So perfect. Yeah, the shape of those struts can change from one project to another. It's again between the architects and the engineers. So you don't need to worry about the shape of whether it's hollow section, circular hollow section, or a plate like that, a PFC channel, it doesn't matter. They will all do the same job. So yeah, make sure you guys understand these elements. That's how you can get back to me with the perfect answers. Because the questions will be about what's the function of this element, why it's like this. It's just like a basic, we don't trick you, we don't give you this confusion questions. It's just the knowledge. You need to know about this system so you know how to build it, you know how to talk about it. This is a real project. I think it is kind of the project you're going to be working on. An assignment one, you can here see in reality the actual column, right? The roof rafters, you can see the haunches. Yeah, you can see in many textbooks the haunches. They got this tapered look, but this may not be cost-wise efficient for the manufacturers. They say, why do I have to cut it here and then go snap it here? Let me just make it a big section and then reduce it, tick. You know, usually contract and the time spends to do the work, it costs more than the material. So I don't need to go and have the look I showed you. It's really up to that's where the construction engineer can come in and say their inputs. Yeah, like this one may cost more because you have here to have two pieces, obviously, but here you can have one piece and then go connect it with another one. It's also a hunch. But they may don't like these type of cuts. It's just going to be a lot of offcuts. Because then what you're going to do with the other member you took from it. So, but maybe the architect, they just like this look. It's really, that's where decision can be made. And it's up to, and they're both doing effectively the same job. That's what I'm trying to tell you. These are the bridging, the fly bracing, the fly braces. I think the bridging cannot be seen. I'll show you bridgings later. But here are the fly bracings, which you all know what they do, and you have to know that there's a lot of questions about them. These plates or cleats, they are the ones which will carry the girts, right? And the girts will be running through here. These are about 8 meters or 10 meters from this point to this point, so it's a lot. This is the wall bracing, the roof bracing. You can see they already placed them. And here behind there, see this dark gray? This is the eave strut, right? This is the eave strut, which will carry the girts. So yeah, spend a few minutes to really see in reality how things look. And you start building. Yeah, so I think here this drawing is kind of continuation for the 3D image I showed you before, to let you understand more about the lapping that I just mentioned to you. You can see the purlins or the girts, they typically open channel. Open channel, they're not like a rectangular hollow section like this, or a circular hollow section. These are called hollow sections. A circular hollow section like this, or a rectangular hollow section like this, or a square hollow section like this, we call them hollow sections. The ones we use in the purlins, we use them as open sections. Why? because if you have a hollow sections, you cannot lap them. One of the reasons we use, because with the Z, you can see Z, you can place it on top of the other Z and lap it. Same thing with the C channel. Just to talk about this as well, the steel materials we use for the purlins or the girts, they are actually lighter. We call them cold formed steel. Basically, there are two main types of steel in the construction market. One is the heavy steel and one is the lightweight steel. The heavy steel, we use them to build the columns, the rafters, the haunches, the struts, eaves, the struts, the bracing. Yeah, they can be small or big, but when we say heavy, they kind of not cold formed, they are molded, right? So they are rolled sections. They call them as well in the textbooks rolled sections. So they are like manufactured in the mold or rolled through machines, heavy machines. Okay. However, the cold formed steel structures like the purlins, they're much lighter. How they do them? They actually done as plates. Okay, and then they can form them in the shapes we see. Let me, if there are nice images I can share with you to really understand cold formed steel construction. So you know what I'm talking about there, just to see an images. Now this is actually, I should say manufacturing. This is just an image shows you where like all those, even you see them in the residential industry, all those type of steel, they are light steel, cheaper, lighter, they are cold formed, right? They're not the hot rolled. So let me say manufacturing here, like manufacturing process, just so you understand. Here we go, like they come as plates. Here, this helps me. They come as plates and they get into machines, and those machines gonna form them in the Z channel or the C channel that we are using in this. So we use which we will talk about soon. Okay, the hot rolled steel. Let me put here hot rolled steel. No, they are the heavy steel which we use. What's this? No, it's not. Oh. Yeah, here we go. They are like, they have more heavy duty. They come as melted steel and they get molded in the shapes or actually rolled into the shapes you want them to be done. They are heavy steel, the steel we use, like the PFC channels, the I sections, all those. So you just need to understand steel is not always a steel which you would expect we're talking about. I think it was a good time for you to understand the differences. This steel is the heavy, expensive steel, and these one are the light, cold formed steel. Now, this drawing or these slides here now is talking to you about sheeting steel. All right, sheeting steel. Yes, sheeting steel, they are initially specified by the architects. And there are different types of them, to let you know, in the market with different models and names. And one of the they are one of the manufacturers who actually manufacture the sheets and also manufactures the Z and C purlins or girts. Just to let you know, as a construction consideration, the main thing you need to consider is understand what type of loadings. To let you know, these sheets, they come in different profiles. Some of them are strong and weak in terms of resisting life load. If you want sheets that will actually carry some sort of heavy duty services loads, they can go up to 3 kPa, 300 kilograms. Then you have to go to strongly profiled cold formed sheets. If not, you can use cheaper, like for residential. We don't expect heavy duty services, like there is no air conditioning units. I know air conditioning units, they have their own steel structure, but still you have the cabling and wiring that will be laid on top. Maybe heavy winds will require you to have strong sheets. So Yeah, I can tell you the engineering drawings, they don't specify these sheets. The architects do, but as a construction engineer, you always need to read what was the wind load, because the engineer in his front sheet, you will put what's the wind load expected on the sheets on the building. Then you can see that wind rating and then make sure those sheets can take such pressure from wind. That's some of the checks you would do. All right. To make it clear for you guys, I just want you to understand sheetings. Yeah, it's part of your budgeting and planning and constructions. There are also documents for you to select what you want to use. In terms of placements, they simply come with the part like 600 width and running typically for up to between 6 to 8 meters. So you put them over the purlins. So sheets basically they are sitting on the purlins. If you look at this image, these are the purlins, and your sheets will be running same thing here. These are the sheets, the green color. These are the sheets. It's up to your transportation. They can go between 6. So they're gonna, and also they're gonna be lapped with the next sheet you have there. Okay. We will not practice the span tables, but it's in terms of how to decide on the size of the sheet. It's gonna be something similar to what I will show you for selecting girts or purlins. There are documents which can be easily used to decide on the profile and confirm it. I can tell you 80% of the project, the architect will do that work. So the architect on his or her drawings will write, use this type of sheet, full stop. That's all you need to do. Okay, so that means, but if not, you just need to go through some manufacturer's tables and decide on, because it depends on the span, how far the purlins are. If they are 900 spaced, you can have particular type of sheet. If the 900 goes to 1.2 meters, like bigger span, then the sheets needs to be stronger. Okay. And these notes will give you ideas about the considerations you need to worry about. Depends on whether you are in cyclonic windy area or not. And there are manufacturers data, they got their own engineers. So the manufacturers, they got their own civil engineers, structural engineers that will be designing and making the span tables which you have available. But with what I'm going to be practicing with you, so this is just an example for a span table that will help you to make a decision on which sheet to use. So this product, clip lock 406, this is the limit state wind pressures it can take. Right. So as I said, the engineer on their engineers going to write down the KPA from the wind. All right. Basically, you just need now to figure out if the purlins was spaced, if the purlins, these guys, see the purlins here? So again, to clarify things to you, these are the roof rafters. On top of the roof rafters, you got Z or C purlins. What the purlins carries, you got carry the sheets, which we're talking about in this page. Okay. So if you know the pressure for strength or the pressure for serviceability, then you can decide which you can decide on this type. So this type, if your pressure was less than, if your ultimate pressure was less than 3.6, these sheets can work at this spacing. Okay. If the spacing is bigger, then the pressure gonna reduce. Obviously, if your pressure, what I'm trying to say, if your engineer put the spacing of the purlins at 1.5 meters, right? And the pressure was 3.7 or 3.6, you cannot use it because they're telling you the maximum end span. Just to let you know, end span is this span here. This is the end span. Okay, so because the sheet here is continuing, this is usually the end span. It works harder than the middle span. or the internal span. The internal span, it's here. The end span is here. The last span, whether this side or this side. First, the single span, if your purlin, if your sheet was actually running from one point to another, but this is not likely. You won't have just single sheet running from one point to another. So usually end span is critical. That's why you can see the pressure at end span. It's less than the pressure at internal span. Now someone will tell me, why should I not go ahead and check for this? It depends. Maybe sometimes engineers change the spans. So for practicing or decision making, you have to go through all cases, and maybe you go with the worst case scenario. The engineer again will give you the service pressure. Service will control the sagging and deflection to be acceptable, and the strength will control the failure. If you met the strength limit state, that means you prevented failure. If you met the serviceability limit state, that means you prevented too much sagging. Any question about this table? So again, this table, you can use it to decide whether this type of sheeting is acceptable or not. So the question like here, can be, or like in real work, is find the most economic sheets to use. You may have, let me see if we have more examples. Here we go. You see here, you got different type of sheets. And the types really gonna determine how strong they are, and as you go stronger, they're gonna be more expensive. So because even those sheets, they come up with different thicknesses, so it's less steel to use. BMT means it's the thickness, it's the base material thickness, BMT. These again documents which I shared with you, or you can find them for free in the internet because the suppliers give them to building practitioners. You can use them. BMT means the base material thickness, and you can see starts with 0.42 mils, and you can go up to 0.8 as well, right? And each one will have its own capacities, say minimum recommended spacing. So it helps you to make sure what you're building is correct. So these sheets, these drawings, I think we got more points here to, helping you to know how things are built. This is again snapshots taken from the manufacturer. Because you're going to buy their products, they show you all the steps. And they said if you followed our steps, and if you got hired contractors, licensed, usually as a practicing engineers and construction engineers, you just need to make sure the document is followed. So basically, to take away liability and responsibility and insurance and all that, you can always take a licensed contractors, like roof plumbers maybe, who got license and their own insurances to get the job done. There are a lot of people who are not insured that can get this done, but the price is going to change. That means you have to control it. You have to control the quality of placement and read the documents. So as I said, the sheets have to be lapped together, as you can see, and then fixity have to be done as per their advices. Yeah, they're telling you what to do and what not to do. And it really varies from one product to another. Okay, basically they use very lightweight tools to put the screwing in, but they have to be within acceptable quality, because all those screwings, they got special screws that are waterproof, obviously, and they got some type of rubber below the head of the screw. So it's really well-known practice in the industry, but again, selecting the material have to be ticked off and checked by the construction managers to make sure qualities are on top. So those 3 or 4 sheets from 1, 2, 3, 4, they basically talking to us about the sheeting products, which covers the warehouses we're talking about. Yes, they won't be engineered by you, by the structure engineer. The structure engineer who do the structural drawings, and I share with you in many projects, They don't talk about them. The architect will specify them if they like special look or special, because some of them, they are actually related to fire rating or related to sustainability, like they call it energy report. Some of them can resist the heat more than others. So sometimes architects want to specify the sheeting. But as a construction consideration, make sure it is built correctly. Make sure the sheets are spanned to the right floor, because the architects are not engineers. And if the structure engineers did not talk about it, that means they're not responsible. You are the construction engineer. You have to make sure where, if you're going to build something, the span will take it, or like it can be spanning or acceptable within that span. You have to, again, to build it, screw it, and do all the requirements in line with the product's specifications. All right. And the architect will tell you that. The architect will say, use clip lock 406, all installation to be in accordance with manufacturer specifications. That's it. So you just need to know. You need to know putting those sheets, they need to be quality controlled. Right. That was about the sheeting. Any question? No hands up, no questions. Good. So we can answer any questions we may have there. Purlins, girts. I talked about them many times over last week, and you know what they are. You know we use them at roof, and you know we use them at the wall, and you know they actually carry the. But questions I like to ask, which I will ask you now, guys. I will answer half of it, or like part of it. You answer the rest. I will tell you, describe or list the function of a C or like a C channel in a warehouse project, or like I give you an image like this simply, yeah, and it's gonna be a zoomed, like more clearer image, and I tell you like this one, like a picture, and I show you. It's gonna be like a clearer picture, like closer, as we're gonna see later. I will tell you, clarify what is the function of this purlin. One of them, I'm telling you now, is to support the sheeting material. Number two, tell me, what's the second one? That's a question for maybe 3 marks. Or what's the function of the purlins? And I will be like zooming into it with a clear picture, like I will highlight this purlin and tell me what are the functions of this purlin. Number one, it is supporting the sheeting materials. Just half a line, tick, that's one correct. What's the other one?
Transferring the load from sheeting material to the portal frame.
That's what I said. So that's the same answer for my one, isn't it? Isn't it? I've already
Yes.
said the purlins, they are supporting the sheets. And you just said it is splitting the load from the sheet to the rafter. It's just the same answer.
Okay, okay.
But there's another job for it. There's another important job we talked about last week. And we answer it. You want me to answer it? If the purlin is not there, and I will highlight this to you, will the fly brace work? Yes or no? If the purlin is not there, will the fly brace work?
No.
No. So the purlins, they are the guys who are going to be restraining the rafters through the portal
is-
frames, through the purlins. Say that. What was that?
No.
Yes. So the answer I was waiting for, the purlins are also restraining the bottom flange of the rafters through the fly brace. That's it. Because as we said, when the wind gonna be pushing up, because they open the doors, pushing up, especially during construction. Like you can see the situation here. I know they didn't put sheets, which that means less loads, but still the wind, if it's really blowy, the girths will be, the purlins will be pushed up slightly. What does that mean? You're actually causing a pressure on the rafter. The rafter is tending to pre-camber like this, to be pushed upwards. When it's pushed upwards, the bottom flange will be under compression, right? And as we said, steel flanges or sections in the steel, they are sensitive to compression. They can buckle. Stop that buckling, we're gonna fly brace it. Fly bracing is actually supported by what? The purlins. So that's their second main important job in the frame. Okay, yeah, actually you can see it here. If I zoom in here, yeah, you can see this is a purlin. This is the roof rafters, and you can see here the fly brace is just gonna stop it from, as I said, this flange. If the beam is flexed upwards, this flange gonna be under compression and it can buckle. Stop it from buckling, I will just restrain it, hold it from at this point, at this. So yes, not all purlins got fly braces, but in that question, I will highlight, I will tell you this purlin, what's its, what are the functions for this purlin? So number one, it supports the sheets. Number two, it is restraining the roof rafters. So that's really the thinking we're talking about. So yeah, we talked about, we have two famous shapes, C and Z. Usually Z is much stronger. The Z one is stronger, and it just depends on which string. Sometimes the look, sometimes there are some other like service considerations we will talk about. All right, those C or Z, they come in different thicknesses. Obviously, we go with the thicker if we need them to take larger spans or stronger pressures, etc., etc. Okay, and as I said to you, the girths or purlins or these sections, they are cold formed steel. They are lighter steel. Now, same as the story on rafters. If you try to bend the section, always the compressed side, if we bend this, for example, if we bend it like, let me just use the pen. If we bend it with a positive bending like that, yeah, so we have compression here and tension there. So what's gonna happen to this side? A flange, it will be compressed and will tend to what? To buckle. It will tend to, which is same problem as for the rafters. To make it more efficient and not really go to bigger sizes, we use what we call it bridgings. A bridging is just, this one is a bridging. You see this element here? This one? I will just clean this to make it. So this, let me use the highlighter. So this element here, it is actually the bridging material which we can tension up to make sure it's working with the correct limit. So what they do, they actually located very close to the top. So again, this is the C channel. You see, this is the C channel. And as I said to you, when it's up in the sky, and it's under flexure, it's compressed side. So usually if it's got positive bending, especially mid-span, this is going to be under compression and this is going to be under tension. The compressed side is a problem and it will tend to buckle or twist. To stop that twisting, we use those bridgings to keep it in position. If you don't do bridgings, you're going to end up using taller or bigger purlins or girts. So that's really the concept of using bridgings. One of the important features that you need to use them in answering your questions and know what to do. Okay, and that was the question I was answering you already. So bridging is just a piece of steel which got those buckles. They simply going to help you to, because usually the spacing when you build this, even if the engineer said put them every 900 or 1 meter, they won't perfectly get it in that. They will just be, say, 1 centimeter or a few millimeters here. So you can't really build the bridging in a single span like length. You're going to do a lot of cutting and that costly work. So it is kind of adjustable in terms of the length to make sure it fits a lot of situations. Okay. So in summary for this slide, girts and purlins, you know what we use them for and their jobs. To build them efficiently, we use bridging. So you don't need actually to go and use bigger sizes for higher wind pressures or longer spans, right? This image just helped you. Again, these images are taken from the industrial documents, which I'm sharing with you. So this is the industrial document from LISA, which gives you all the construction techniques in terms of design or even installation. You may need to focus on installation because, and design, again, as we're going to say, it gives you all the span tables, it gives you all the detailing. And one of the things we're going to practice together, it is deciding on the size. And basically what we do here, we use these kind of span tables. They are very simple tables, but I just want you to know, because sometimes engineers don't specify them and they leave them to the construction engineers to decide on them, which I will give you a quick talk about it as well. All right, so if I go back to my lecture notes, just to continue, yeah, as I said, these diagrams, they are very helpful. They help the contractors to determine how much lap, now up to us to decide whether it's 0.5 meter or there is a particular size of lap. As I said, we lap above the support, which is the roof rafter here. We lap, that will help us to let the section take more bending and flexion. Take what I mean section, I'm talking about this section, the purlin or girt itself. So we lap them again because we can't have very long meter girts or purlins or to cover our development. So we need to lap them. When we lap them, we have to make sure they are adequately lapped and bolted to get the system to work. Okay. This type of jointing, again, it means that you stop the beam, but it won't be efficient. All right. Maybe you're going to be in a situation where you need to stop and start. If you end up with situations, you may end up having stronger sections, larger sections, but I'm not sure why you need to do that. There are different ways and reasons where sometimes people may actually put this C channel at the lower side, like facing the C is facing downwards. Sometimes the C is facing upwards. That's really architectural decision, or again, it's just going to help with the cleaning, as we're going to see in the next few slides. Usually the C channel, this is easy to clean, but it's got its own, it's difficult to build. Right, we're going to talk about this in a different slide, but I'm just saying it here. Can someone tell me why this is difficult to build quickly? So I'm telling you, this is easy to clean. People can just spray water and just clean it with a mop or whatever from someone standing from below. Okay, and this won't be collecting rubbish over time or dust or whatever. However, it is difficult to construct. Did it make sense? Why? Because, yeah, if you put something on top, it's just going to sit on top. And then it's going to be easier to screw. But here you need someone to lift it up and keep lifting it until someone put the screws. Okay? This is, again, that's where you have to look at the contracts and the engineering drawings and the architectural drawings, what they are showing. All right, that's how you need to guide your contractors. Maybe nobody's maybe the engineers did not talk about how to put them because it does not really matter a lot for engineers. Architects same, but you don't want your contractors to go and place them like this because it will cost them days and you're going to pay for those days. You can actually let them guide them to do it differently, and that will save you days, right? Now, as I said, whether the C channels or the Z channels, they are designed by engineers. There are engineers who work for LISA who really design those shapes and profiles to get them rolled. That's how they are rolled out as a cold steel form type, and they come up with capacities. Okay. Now, to make it easy for the construction engineers, they give us tables to read the spans of flow. So before we look at the tables, there are different type of spans, depends on your project. Sometimes you have a single span, which you know from university and engineering learning. Sometimes you have only 2 spans, sometimes 3 spans. If you have 1 span, we're going to have only 1 type of bending, if you remember when you did this. So here the bending going to be positive, that's it. If you have multi-spans, like 2 spans, you're going to have some, you're going to have positive, then negative at the support. If you have 3, same thing, you're going to have positive, negative, positive, negative, positive, and 0. Okay. Now, sometimes if the building is very long, you cannot actually have 1 piece. Maybe you can't transport it. Usually warehouses are located in a distance areas or locations, and it's maybe difficult to get a long truck to go there. So you can decide on having smaller sections, but remember, you're going to be paying more for doing the laps. Okay, so this image really, it tells you the type of spans available for the builders and construction engineers to plan on building the warehouse. There are different spans arrangement. Just pay attention. There are 2 types of continuous. There is a lapped continuous, and there is just a single piece, like the own piece is actually continuing. There is no lap. Okay, it depends again on are you able to bring long trucks into your site. Maybe sometimes in the city you can't bring very long trucks. It's very expensive and slow for them to maneuver and turn around and do all these things. So usually you can bring those sections as in smaller spans and then just do the lapping, but that's the only best option you have. How to decide on the purlin size is by using these tables, and that's what I want to practice with you. And yeah, it is likely to have such questions in your exam. So for example, I may give you one of those spans and I give you the span value and I tell me what's the most efficient purlin to use. So let's do it quickly together, guys. Yeah, time is ticking, so we may have a break and then we talk about the workshop questions. Let's say this is what you need, how you construct. You can't get very long trucks. You have to have small pieces. And let me tell you that you have to lap them. Okay. And so in the question, I may not tell you even, I may give you this image. I will tell you decide on which. I will tell you you have a 3 spans for your purlin, and it is not possible for you to deliver a truck longer than particular distance. Like what I will tell you the span here is about 6 meters. Let's put it down together. Let's do this exercise. The span is equal to 6 meters, right? And I will tell you in the question that you are not able to bring more than 7 meters long or 8 meters long purlins, because transportation does not help you there. So the maximum length you can get, maximum length is actually 8 meters. Okay. All right. I will give you a pressures. Let's say you got 3 kPa wind pressure. Give you everything. All right. And I tell you, decide which is the most efficient purlin size you have. And I will give you tables. You're going to be given few tables, not one. And in this case, you would need to run through the tables and you need to look at the, okay, I think in this table, we did not give you continuous. So let's look at the document that you will be having table from this document. So have a look here. This is single span. So no, it does not help you. This is single span. It's not your problem. You have a little image here really, which is helping you. Yeah. So keep flipping. Keep flipping. This is again, yeah, it is 2 spans, but does it answer what we want? Quickly, guys. Yeah, do you think it will answer what we want? Can we use this? Can we use it? No, we can't because it's not 3 spans anyway. You will be given it's 3 spans and lapped. So you keep flipping through the page, and this is basically, this is 3 spans, yeah, but they are continuous. This is continuous lapped. So that's the table you would be using. You got 3 spans and they are lapped as well. Okay, then I've told you already your span is about 6 meters, right? Your span is about 6 meters. Okay, this is the Z. And this is Z as well. I think you have another one talking about C. Let's have a look. Here we go. You got here Z or C. It's up to you. So these 2 pages got more here, and it's talking about Z. So they go higher, right? But let's have a look here. Can we have the smallest section? The smallest section you would find in Z, it is actually 100. Okay, 100 deep, right? And the pressures, let's say it was given to you as a 3. Now, inwards and outwards, as I said, they are the pressures from outside to in or from inside to out. If the door was open, it's going to be inside out. That means inward. And basically, you're going to be given one figure, whether indoor and outdoor. So you need to make sure it covers both. Okay. So obviously, I said to you, the span is 6 meters. Does it work? So the pressure going to be given to you in kilonewton meter. Does it actually work here? No, it's not. If I'm telling you it's a 3, it definitely does not work. 6 meters is a lot, and it can only take, you see the worst case scenario here between inwards and outwards, whether you use, guys, these are the number of bridgings. We can have no bridgings, 1 bridging, 2 bridging, or 3 bridgings. That's in that span. In the span we're talking about. So bridging means they are the elements I did show you. And if we're talking about 1, that means it's 1 in the middle. If we're talking about 2, it means that we have 2 equally spaced, always 2 bridgings. If 3, yeah, it means we have 3, again, they are equally spaced. Okay, so you can see whenever we have more bridgings, it can take more pressure sometimes. This depends on the calculation. Sometimes it does not matter. You can see in this case here, it does not really matter. And yeah, see here, it starts like if we go to 6, you're going to have more pressure to take. It goes up and up, right? But anyway, it looks like when I said the number 3 for you, this table or this size, which is only 100 millimeters high, with 12 millimeter, with the one, I think 12 means the thickness, but it's not 12 millimeters a lot. It's maybe 1.2 millimeter. It's not helping. So you need to go to bigger sections. Let's see if it's really take up to 3, but it looks like it's struggling. So maybe we can't. That's it. 3 laps, 6 meters. Here we go. Yeah, we start sensing something. Here we go. we start getting, yeah, you see here? You start getting, you can use 150Z with 1.9 thick wall, like the thickness of the base material. And you can say 6 meters can take 3 kPa here, right? You just need to use one bridgings. Okay, so this document is available in your LMS as a reading material, and this table can help you to make a decision on the most efficient section we can use. And I can see Z section 150 deep. So the first letter here is the shape. This number here, the first 3 numbers, gives you the depth. And this one, talking about the thickness of the steel. You've got different thicknesses. And if you need to read those carefully, you got at the start of the document, it talks about such information. Okay. Strongly suggest you to look at those tables. If you have any questions about them, let me know during the workshop or when we meet, depends on on-campus day. Do you have any questions about using those tables? You need another example, that one when you can let me know. But simply we call them, they are span tables. And this, yeah, they got different types, but the one we're gonna practice, or you may be asked to use, it is the PDF document you have uploaded to you. This is an older document. All right, so there are some construction considerations which you may pay attention to. We got about 5. Let me finish those slides, about 4 slides, and then we stop the lecture. So as I said, there are very nice notes I would like you to pay attention to, which kind of let you know the construction advantage from placing the C. This is the C or Z purlins. This is the C purlin. This is the Z purlin. Sometimes you can put the C channel above the cleat, which, as you know, it's easier to, this is difficult to clean, but it's good stability during construction, obviously. Good stability during construction, because obviously it's just going to be sitting on something while you are placing the channel, but it's difficult to clean. That's the standard mode. There are other modes where you can put it at the low side, but it's, yes, easy to clean out in case this structure was kind of a theater or something that it needs to stay clean, or it's not the, you know, it's kind of more habitable environment. Then that's where the right decision can come in and be done. You know, but there are standard modes, which just kind of the manufacturer. Again, this kind of recommendation is not from the engineers, it's from the manufacturers who do the Z or C channels, those cold form channels. Okay. And as you can know, when you have a steeper roof, it's going to be more difficult to place the purlins or channels than having a flat roof. And then that's where you may be stuck in using the stability reason, because it's easier. Same thing I was talking to you about the girts, same story with the girts. So that was here about the purlins. It's got advantages of placing the section above or below the cleat, the fixing plate. Same thing with girts. There is advantages or disadvantages when we place the girts above or below the cleat, which is a piece of steel that's welded to the column. The column is basically this side, right? And you've got cleat, and you will be fixing the C or Z, depends on the reason. Now, someone will say, should I go with C or Z? Depends on the strength. You're looking at the tables, and depends on the strength, which one can do the job. The manufacturers provide a standard mode of this, but this one, as you say, is going to be costly with time. It's difficult to, it's easy to clean out as a durability and long term, and you don't need to put screens. You know what screens? If you're going to use this option, you have to make sure that, especially in, because these warehouses is built especially in the middle of the farms. Yeah, that's where they're going to store all the vegetables before they deliver them to Woolworth and Coles, so we buy them. They don't bring them to Coles on day one. They put them for months in the warehouses. And sometimes you need to make sure that nothing gonna be living here, no animals, or they talking about, yeah, you have to put special screening, whatever, which is again cost. That's why, now one of the reasons why we look into those details is, which are very costly and important for construction engineers, is when they read the job project and kind of want to find out how complicated it is, how costly it is. These details make a lot of difference. If you don't know about this and you find out you must build it like this and you must put sheeting, then you have to allow for that with your price and time. Okay, there's another points you may need to know about the centroid. There is like one of the reasons why the Z purlin will work better, because I did mention to you Z purlins works better, stronger than the C, and C obviously going to be cheaper. It is because the eccentricity, usually, as you know, you see the section is placed unevenly. It's on a slope. So effectively, design-wise, that means there is kind of eccentricity between where the load gonna come from the sheet. We all know our wind load. So the load from wind or the dead load or the sheet gonna be placed here. That's where you're gonna screw it. You're gonna have special screws, which I talked to you. The sheeting people gonna tell you how to screw it. You're gonna screw it here, and effectively the load's gonna come here. Now, engineering-wise, the eccentricity from this line and this line is only this much. If you use a C channel, the eccentricity will be more because the centroid of a C channel is outside. The centroid for a C channel is outside the shape. Okay, is outside the shape. But here, the Z is kind of helping you to correctly distribute the mass, or the line. It's kind of distributed equally around its vertical axis and around its horizontal axis. But the problem with C channel, both of its flanges are facing one side, so its centroid is always in an odd location. What does this mean? You're going to have larger eccentricity between the line of action and the centroid. That will cause more stresses on your on your section. So that's why you end up having more. And again, it depends on how you're going to be placing it. Okay, it depends on how you're going to be placing it. If you misplaced the Z section, you may be in the same issue. Okay, and that's where I think these are one of the critical, which can be easily missed. If you've been deciding on placing your Z sections in this direction, you just need to double check, and it can happen sometimes where this is placed in the wrong direction. That means it's going to be weaker than expected. The solution for this, it does happen in many cases, you're just going to may need to put more bridgings. Instead of 2, you may put them 3. Instead of nothing, you may put 1. You're just going to add more bridging to let it work. You know, the bridging elements I was talking to you about. And yeah, we're re-talking about it again in the last 2 slides. So I did talk to you already about them and the job of the bridging and how they're going to help restraining the purlin or the girth to give it more capacity. Okay, and these are the bridgings. So as I said to you, the bridging is just going to be running between one purlin or girth to another. And most likely you won't see them in the girths because the girths got the holding down bolts. You will see the bridging in the purlins in the roof, and there are different types. You've got this type, or like lightweight, or this one. It's again whatever comes from the manufacturers. Okay, and this is again just from the manufacturer, from the same document, which can give you different ways of fixing the bridgings to your. So these are your purlins lines, and just here is talking about those bridging elements. They look complicated, but they are like this element here. It is same as the one I showed you in the picture just back here. This one. This guy I was talking to you about for about 2-3 minutes. It is simply just this example here, this element. And they're telling you it's up to you. You want to use this in different places, it's your choice. Right? Usually these kind of decisions, the supplier, he will organize it for you. Because you're going to go to them, give them your engineering or architectural drawings, tell them supply all this roof to me. And they're going to give you a table, schedule, guidelines. They're going to give you even this document I shared with you to use and read, and that's it. You just need to manage the process. And usually contractors are licensed, they know what they're doing. They're just going to tell you, give me 3 days and I will give you a certificate which tells you all done, which will give you a peace of mind. Okay, that's really how things can work, but you need to know the knowledge. You don't need to be driven in the wrong way. Maybe, as I said, one of the key mistakes which nobody will pick, and if it was picked, you need to compensate. So a mistake like, for example, the one I just told you, if it was specified to put a sheet here, or if it was specified because the architect really want to clean them out, the architect want the purlins to be like they want to see them, and they want them to be placed like this, not like that. That's where you need to know that knowledge to make sure what's happening is what's in line with the architectural intent. Because if it's missed, you simply, some of the project will tell you, don't give me any compensation, don't even give me better coloring or better lighting, or go repeat it, and that's a cost. This will blow up your bill. So guys, yeah, 9:30. I think, yeah, we finished the notes. Is there any question? So I think I've given you all the knowledge you need to know about the details that you need to consider, whether construction details and design considerations, to understand what portal frames are, what's the secrets behind them, what people look at from a construction engineer perspective. There are much more to learn from site, and we're going to learn more as well from our workshop as well this week. And you're going to be working on this workshop over the weeks until submission, which I briefed you about the assignment carefully last week. Yeah, I briefed you about it during the workshop, but I did not start answering questions. So before, I will give you some few minutes as a break. Is there any question you want to ask about portal frames lecture notes? Is there any question about portal frames, or like, do you want to more examples? Let me know. But even if I don't have time to do it today, I can think about that, like plan a day, plan some time to do it during the workshop. So what the best way of really learning this, even if you feel it's simple things to know, don't leave it until the final exam. It's going to be a lot of information on your minds. Print these slides or save them, and electronically or as a hard copy, put the notes we discussed, because that's how I'm going to ask you. If I didn't use a learning material, if I did not talk with you about it, it won't be coming in the final exam. But there's a lot of things I talked about: practice, ask questions and answer them. These are the sort of questions will be very similar to what you're going to see in the final exam. So I will wait for 10 seconds. Is there any question or you have about the topic, portal frame topic. Look to those links, they give you good, you may visit them. I show it to them during the workshop. They just let you see, I think one of the suppliers, they're going to talk to you about installation and all those techniques. Any general question about the subject? Not about the topic?